let's talk about Enceladus. All right, this is very cool. This is a moon that we've been eyeing. All right, we've been looking at this moon for some time. Here's one of the things that kind of started it. Right, science discovered 101 geysers on Enceladus. A team of U.S. researchers using data from NASA's Cassini spacecraft have discovered 101 active geysers erupting from Enceladus, the sixth largest moon of Saturn. Saturn is actually the first planet that I viewed in my own eyes. When I was living in New York City, I lived there for 12 years, and in Central Park, every Saturday night during the summer times, if you live in New York, you should definitely check us out. I don't remember exactly where it is, but it's somewhere in the middle. I want to say around 80th Street on the east side of the park. There's a smallish meadow that this crew sets up telescopes, like serious telescopes. They are dope telescopes. And one night, it was very clear when I was there, and Saturn was there, and everyone was like, "Oh, Saturn, you check us out." And I looked through the telescope and I saw Saturn, and it was incredible. It was pretty awe-inspiring to see Saturn with my own eyes. Like, that's Saturn. That's the planet. I could see the rings. It was really something to see. Anyway, back to the story. After the first sighting of geysers on Enceladus in 2005, planetary scientists suspected that repeated flexing of the moon by Saturn's tides as the moon orbits the planet had something to do with their behavior. One suggestion included the back-and-forth rubbing of opposing walls on the fractures generated frictional heat that turned ice into geyser-forming vapor and liquid. Alternate views held that the opening and closing of the fractures allowed water vapor from below to reach the surface. To determine the surface locations of the geysers, University of California and Space Science Institute scientists employed the same process of triangulation used historically to survey geological formation or features on Earth, such as mountains. When they compared the geysers' locations with map of thermal emission, it became apparent the greatest geyser activity coincided with the greatest thermal radiation. Comparisons between the geysers and tidal stresses revealed similar connections. However, these correlations alone were insufficient to answer the question, what produces what? The answer came from comparison of the survey results with high-resolution Cassini VIMS data. The individual geysers were found to coincide with small-scale hotspots, only a few tens of meters across, which were too small to be produced by frictional heating, but the right size to be result of condensation of vapor on the near surface walls of the fractures. This immediately implicated the hotspots as signature of geysering process. Once they had these results in hand, we knew right away heat was not causing the geysers, but vice versa. It also told us the geysers were not near surface phenomenon. They have much deeper roots, says Carol Porco of the Space Science Institute in Boulder, Colorado, which is the lead author in the paper published in the Astronomical Journal. Okay, so that's the geysers. Okay, and that was from 2005 where they were doing this study. This came out in 2014. Now, this article came out today. Check this out. So now we found out that there is a subsurface ocean that has currents. Now, we knew about the ocean, but we didn't know that it had currents. So check this out. All right, well, it's a theory. The novel theory proposed by planetary scientists from Caltech and NASA's Jet Propulsion Laboratory challenges the current thinking that the saltwater global ocean of Enceladus, the sixth largest moon of Saturn, is homogeneous. Let's see here. In 2014, this is what I was talking about, Cassini spacecraft discovered evidence of a large subsurface ocean on Enceladus and sampled water from geyser-like eruptions that occurred through fissures in the ice at the South Pole. It is one of few locations in the solar system with liquid water, making it a target of interest for astrobiologists searching for signs of life. The ocean on Enceladus is almost entirely unlike Earth's. Almost. Earth's ocean is relatively shallow, covering 3/4 of the planet's surface, is warmer at the top from the sun's rays and colder at the depths near the sea floor, and has currents that are affected by wind. Enceladus, meanwhile, appears to have a globe-spanning and completely subsurface ocean that is at least 30 kilometers deep and is cooled at the top near the ice shell and warmed at the bottom by heat from the moon's core. Despite their differences, Caltech graduate student Anna Lobo and colleagues suggest that the Enceladus Ocean has currents akin to those on Earth. And here's a really cool image with a slice cut out of it where you can see the ice outer shell with actually the fractures and the geysers coming out, and then the subsurface ocean there. Very cool. The oceans of Enceladus and Earth share one important characteristic, and this is huge. They are salty, okay? And as shown by the team, variations in salinity could serve as drivers of the ocean circulation on Enceladus, much as they do in Earth's southern ocean. Now, I'm going to come back to this image in a little bit. Gravitational measurements and calculations from Cassini had already revealed that the ice shell is thinner at the poles and then at the equator, said Professor Andrew Thompson, a researcher in the Division of Geological and Planetary Scientists at Caltech. Regions of thin ice at the poles are likely associated with melting and regions of thick ice at the equator with freezing. This affects the ocean currents because when salty water freezes, it releases the salt and makes the surrounding water heavier, causing it to sink. The opposite happens in regions of melt. Knowing the distribution of ice allows us to place constraints on circulation patterns on patterns, Lobo said. The team's computer model suggests that the regions of freezing and melting identified by the ice structure would be connected by the ocean currents. This would create a pole to equator circulation that influences the distribution of heat and nutrients. Nutrients. I'm going to come back to that in a second also. Understanding which regions of the subsurface ocean might be the most hospitable to life as we know it, it could one day inform efforts to search for signs of life, Professor Thompson said. Now, that is the key here. I'm going to open this image to zoom in on something. Check. This is what I can't get over. Come on, let me over there. And slowly moving to that. What do you see there? Those are vents, right? Where's that heat coming from? Well, they already said, or what they're alluding to, that it would be the planet's core. Well, where do we see something like that on Earth? It is the deep hydrothermal vents. Okay, you can kind of see it here. I'm not going to play the video, but you could see these deep vents, but I'm going to read about it. Okay, in 1977, scientists exploring the Galapagos Ridge along the mid-ocean ridge in the East Pacific noticed a series of temperature spikes in their data. They wondered how deep ocean temperatures could change so drastically, from near freezing to 400 degrees Celsius, which is 750 Fahrenheit. Crazy. In such a short distance, the scientists had made a fascinating discovery. Deep sea hydrothermal vents. They also realized that an entirely unique ecosystem, including hundreds of new species, existed around the vents. Despite the extreme temperatures and pressures, toxic minerals, and the lack of sunlight that characterized the deep sea vent ecosystem, the species living there were thriving. Scientists later realized that bacteria were converting the toxic vent minerals into usable forms of energy through a process called chemosynthesis. Chemosynthesis, that's probably it. Providing food for other vent organisms. Okay, now knowing that, I'm going back to this. So we have already seen on our own planet, okay, that there can be a thriving ecosystem with no sunlight, or very, very little sunlight. Sunlight can pass through ice. I don't know if there's sunlight under there, but they could get nutrients. That those currents are pushing nutrients around. For all I see from looking at this, That's a large ocean of moving around that, with heat coming from the inside and a solinated ocean. I think there's life there. I think there's life on Enceladus, and I think it's really cool. I think it's very exciting. I don't know what kind of life it is. It might be some alien space shrimp, right? I mean, it would be alien, right? Alien is a life that is not of Earth. I think so. It's pretty cool. I'm pretty excited about it. So I will be paying close attention to all the research that is coming from Caltech. Seems to be doing a lot of the research there. Very, very cool stuff.